Hello, grade 12. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 5. It says an ice skater of mass 53 kg moves on a frictionless surface AB with a velocity of 6 meters per second and then slides up a rough inclined surface BC until coming to a stop. So note that until coming to a stop at point C, 1.5 meter above the horizontal. They say the angle between the incline and the horizontal is theta. And then in 5.1 says state the work energy theorem in words. So this is how you're going to go about it. To define that, we're going to say work energy theorem states that the net work done on an object, is equal to the object's change in kinetic energy. Right, so we have that. States that the net work done on an object is equals to the object's change in kinetic energy. And then if you ever want to remember that definition, you have to look at the formula that goes W net is equals to change in EK. Now we can see that the net work done is equal to the object's change in kinetic energy. Right. Then we have 5.2. It says draw a labeled free body diagram showing all the forces acting on the skater at point C. Note that at point C, the skater would have gone up the rough surface and inclined rough surface. If you can just allow me to draw it up here. And then note that with drawing the free body diagram, you are no longer allowed to show the components. So you need to show the normal force, and then do not break down your gravitational force into components, but then rather just draw it straight down like that. So gravity is always acting downward. And then since this is going up the incline, we know that the frictional force will oppose the ice skater. And then there we go. So for 3 marks, we have 3 forces, right? So note also in your exam that whenever you draw, you must now use your pen and not your pencil, right? So, okay, we have that 1, 2, and then 3. Okay, then 5.3 says, explain the term non-conservative force. What is non-conservative force? Say non-conservative force is a force for which the work done in moving an object between 2 points depends on the part taken. Depends on the part taken. So do not get it confused. When it comes to a non-conservative force, it depends on the part taken, but a conservative force is independent of the path taken. Now, your examples of non-conservative forces are your frictional force, your tension force, and also your applied force, right? So always remember that. So sometimes they might ask you to name the non-conservative force, right? So frictional force, tension force, and applied force are the examples of your non-conservative forces. And then the conservative forces are your gravitational force and normal force. So always keep that in mind. Okay, now 5.4, we have calculate the angle theta of the slope if the skater experiences a frictional force of 20 Newton while skating up the slope. Right. Now, at this point, we can see that we have already collected how many marks? 2 plus 3 plus 2. That's already 7 marks out of 13. Right. So that's a decent mark. So that means right now when we are practicing, we are only dealing with having to master these questions here, right? But then you already know that the other ones, you already have them in the bag, right? So for 5.4, calculate the angle theta. Now you have to understand the nature of a 6-mark question. Whenever you have a 6-mark question, always think along the lines of, I will be trying to calculate theta, but then there has to be something that I have to figure out first before I can calculate the angle theta. So what is that? Having to apply your SOHCAHTOA, which is your trigonometry, you do understand that if you wanted to calculate theta here, you'd have to apply the trig ratio sign, which would be sine theta is equals to the opposite, which is the height, and then over the hypotenuse, which is the displacement. Now, you do understand that you do have the height, which is 1.5 meters, but then you don't have the displacement delta x, which is your hypotenuse side. So which means for this 6 marks, the first thing that you would need to figure out is delta x before you can worry about having to calculate the angle theta, right? So that's normally the nature of a 6-mark question. You need to get something first, right? You need to kind of diverge from the question, get what you are missing so that you can now calculate what you are looking for. Okay, so now let's start with that. Obviously, here we understand that we must use energy principles, right? So how do we choose an energy principle? From here, we can see that they're talking about the skater experiencing frictional force. And then from up here, we were asked to define non-conservative force. Now, usually when I answer these questions, I view this as more like the hint from an examiner to say that use this kind of formula. Because now if you can check in 5.3, we just define non-conservative force. And in 5.4, we must use an energy principle to calculate. Now, obviously, if you can just read between the lines, you can see that there is more of a hint, a giveaway to say that use the formula for work done by non-conservative force. And also to consider the fact that frictional force, remember, it's a what? It's a non-conservative force. So even more reason to use that formula. So that means now in 5.4 to tackle that, can say work done by non-conservative force is equals to what? Change in EK plus change in EP, right? Now, from here, we can observe that our only non-conservative force is what? The frictional force. Again, if we can redraw our free body diagram, remember that we had normal force, which we did state that normal force is a conservative force. And then we also have gravitational force, which is also another conservative force. But the only non-conservative force that we have is Fk, right? Both these ones are conservative forces. So we only have Fk, kinetic frictional force, as the non-conservative force. So that means we can break this one down to Wfk is equals to change in Ek plus change in Ep. But then note that we are looking for a delta x first. So where are we going to find delta x? If we can just break down this here. So I want you to observe this. Let's break down Wfk. It's going to be Fk, delta x, and then cos theta. And then this, when it breaks down, it's half m bracket Vf squared minus Vi squared plus mg bracket height finally minus height initial. Now, I don't want you to be confused about the data that we are looking for. The data that you see in here, that's not the angle of the slope. That's the angle between the what you call the force and the displacement. Note that the displacement of the skater is in that direction. Remember, the skater is moving up the incline, right? And then now when we are looking at the displacement and the kinetic frictional force, we can see that they form a straight line. So that means the angle in between them has to be what? 180 degrees, right? So for here, we're just going to substitute 180 degrees. That's not the data that we are looking for. At this point, we are only just looking for the displacement because we are not given the displacement from point B all the way to point C. And then from finding the displacement, that's when we're going to calculate the angle of the slope. So, okay, let's now calculate. What is our FK? FK is what? 20 Newton is given here. So this is 20. We don't have the displacement, but then the theta here is 180 degrees because remember, FK is doing negative work. And then this is half. The mass is 53. And then a final velocity. Note that when we read there, they said it's coming to a stop at point C. So coming to a stop means the final velocity will be 0. And then initial velocity, they said it moves on a frictionless surface AB with a velocity of 6 meters per second. So at this point from A to B, it was moving at a constant velocity of 6 meters per second, meaning from point A, it's 6 meters per second, all the way to point B, it's 6 meters per second. So remember, our initial velocity will start at point B if we are considering the slope here. So this is going to be 6 square, and then plus, we have the mass, again, is 53. So that's 53, and then 9.8. And then we have the height finally. So at point C, the height will be 1.5. But then at point B, remember that it was on ground level, right? So on ground level, we say the height is 0, right? Now at this point, you just simply need to punch all of this into your calculator. Okay, so now having to punch this into our calculator, this side here, we get negative 20 delta x. And then on the right-hand side, we get negative 174.9, which we can then divide both sides by negative 20. And then our delta x displacement will now be equal to positive 8.745 meters, right? So now we have the displacement, right? If we then now have the displacement, that means we can then use SOHCAHTOA or the sine trig ratio. So now we have the fact that from B to C, it's 8.745 meters. And then the height we are given to be 1.5. So that means we can say sine theta is equals to height over the displacement, which will give us sine theta is equals to height is 1.5. And then the displacement, it's 8.745. Now to calculate theta, you're going to say arc sine and then 1.5 over 8.745. And then you just calculate your theta, as simple as that. So arc sine 1.5 over 8.745. And then punch all of that into your calculator. You get your theta as 9.88 degrees, rounded off to 2 decimal places. And then that's just how you were supposed to tackle that 6-mark question there. So yes, very nice, very demure. Okay, so let's have a look at another one, another question. So here we are given question 4. It says a wooden box slides down a rough 8-meter long inclined plane AB. The initial velocity of the box at A is 2 meters per second as shown in the diagram below. And then the first question is saying, define a conservative force. So what is a conservative force? Note this time around, it's a defined conservative force. Right, so a conservative force, we say, is a force for which the work done on an object moving between 2 points, on an object moving between 2 points is independent. Note this, is independent of the part taken, right? So a conservative force is independent of the part taken. And then in 4.2, they're now saying name a conservative force in the diagram above. Now we know that our conservative force can either be gravitational force or normal force. So mentioning either one of those would be correct. So you would say normal force, or someone might choose to say gravitational force. Both answers are correct because these two are examples of conservative forces. Now we have 4.3. So note how easy it is to bag marks in this topic. State the work energy theorem in words. Again, you remember W net is equals to change in EK. And then the net work done on an object is equal to the object's change in kinetic energy. So states that the net work done on an object is equal to the object's change in kinetic energy. Right. So that's the work energy theorem. So just like that, we already have 5 marks. 5 marks out of 13. So impi isachubeka. Let's go on. Then, okay, 4.4 says the velocity of the block at point B is 6.92 meters per second. Use energy principles only. Note that. Use energy principles only. So that means no equations of motion here. Use energy principles only to calculate the frictional force that the block experiences as it moves from point A to point B. Right? So, okay, now, considering that I am to calculate the frictional force. What is frictional force? I know frictional force to be a what? A non-conservative force, right? A non-conservative force. So I can just simply use the non-conservative force formula to calculate that, right? I mostly I mostly prefer to just use the WNC formula. You can still use the work net formula in this case. So, but then let's just go with WNC because it's just straightforward. Work done by non-conservative force is change in EK plus change in EP. And then since here, if we are to draw a free body diagram between from point A to point B, we do understand that our object, the dot would indicate the object. This would be the normal force, and this would be the gravitational force. Again, I'm not resolving into components. So I'm avoiding resolving into components. I'm avoiding W net formula because I simply don't want to resolve into components. Right. So which is why I'm saying this one is much more simple and straightforward. So this is FK. And now from here, I can identify that FK is the only non-conservative force. That means I can replace this by work done by FK, which will break down to FK, delta X, and then cos theta is equals to half M VF squared minus VI squared plus mg height finally minus height initial. Okay, so now the FK, that's what I'm trying to calculate. But then this time around, I can say that I am given the displacement from A to B. That's 8 meters. And then cos, remember, every time we are dealing with FK, the theta is always 180 degrees because we are saying kinetic frictional force always does negative work. Then this is half. And then the mass is what? 2 kg. Final velocity, let's read the initial velocity of the box at A is 2 meters per second. So that's VI. But then they said the velocity of the block at point B is 6.92 meters per second. So that's V final. So we're going to start with the 6.92 square minus initially it was at point A. So that's 2 square plus the mass is 2 kg, and then we have 9.8. Then height finally, that's the height when it reaches point B. So at point B, it's on ground level. So that means the height at that point is 0. Then the initial height, meaning at that point right there. Now, obviously, we can see it's not indicated here, but that's not a train smash because we can actually calculate it. Remember, we already know that sine theta is equals to a height over delta x, opposite of a hypotenuse. Now, if we want height, we can simply say height is sine theta multiplied by delta x, which we're going to have sine 30 degrees and then multiply by the displacement, which is 8. Now, your height will simply become what? 4 meters, right? So sine 30 is half of 8 is 4. Then we have 4 here. Then at this point, you need the aid of Umshinwe Ibalo, your calculator. So 8 cos 180, that's negative 8 FK, is equals to all of this into your calculator. We have half. So you have to be very, very careful with how you punch your calculator. One mistake, you can just end up with a wrong answer that will just lead to a series of even more wrong answers. So you just need to double check everything that you're punching into your calculator. Then here we have negative 34.5136. So I'm not rounding off because it's not the final answer yet. So if I divide both sides by negative 8, then my FK is that. So that's 4.31. Now I can round off because that's the final answer. Then yes, I have it like that. So my kinetic frictional force is 4.31 newtons. So that's basically what you are supposed to do. So you see with the WNC formula, it's just straightforward like that, not complicated, just plug and play. Okay, now remember I said on an incline situation, the WNC works best, right? If you have height and then it's an incline slope, then it's best to just go with the WNC formula. Now the WNet, I prefer to use it on horizontal surfaces, like the question that we are going to have right now in 4.5. So, okay, let's check. The coefficient of friction for the last horizontal stretch, you see, once they mention horizontal, that's where I get triggered to use what? The work energy theorem. The coefficient of friction for the last horizontal stretch after point B is 0.35. So we are given what? Mu K. And then calculate the distance the block will travel before coming to a complete stop. Before doing what? Coming to a complete stop, meaning before at the point where V finally will be 0 meters per second without using equations of motion. So again, using only energy principles, right? Using only energy principles. By energy principles, work done by non-conservative forces, work energy theorem, and principle of conservation of mechanical energy. But we do know for sure that we can't use principle of conservation of mechanical energy simply because there is friction. If there is friction, principle of conservation of mechanical energy, you don't even dream about it because that only works in an isolated system where there is zero friction, right? So you need to always note that. So meaning we only have the option of work done by non-conservative forces or the work energy theorem. But then since it's a horizontal surface, I will just go with WNet because that's where it works best. So I would say WNet is equals to what? Change in EK. Now note that on the horizontal stretch, this is how our free body diagram would look like. So it will obviously have the normal force up there, the gravitational force down there, and then parallel to the horizontal slope will be your kinetic frictional force, right? Then just like this. Now we already know that the work done by Fn, work done by the normal force will be 0 joules. And then also work done by Fg will be 0 joules, right? To understand this, you can also catch my video where I explain the concept of work energy and power. So, but then the reason why it's 0 joules and then that one is also 0 joules is because the displacement is in that direction. But then if you look at the force and the displacement, the angle in between the normal force and the displacement is 90 degrees. Even with Fg, the angle between the force and the displacement is 90 degrees. Now remember, cos 90 degrees is always equal to 0. If you can calculate work done by Fn, whatever value that we find for Fn multiplied by delta x and then cos 90 degrees, all of this will just end up being what? 0 joules. So we say that if the force and the displacement form an angle of 90 degrees, there is no work done. Remember that, no work done. So vertical forces on a horizontally moving object cannot do any work. So if you have a force that is going vertical, but the object is moving horizontally, then that means that force cannot do any work on the object, right? So basically, the force between the angle between the force and the displacement should never be equal to 90 degrees. So, okay, that means in that case, the only force that will be doing work on the object is what? Fk. So here, obviously, if you want to break it down, this is work done by Fn plus work done by Fg. Remember, W net is a sum of all the work done by the forces that are present on that particular object, plus work done by Fk is equals to what? Change in Ek. But then remember, these two are not doing any work. It's 0 joules. So that means we are only left with what? We are only left with work done by Fk. So I'm just stretching it out so that you understand, right? Otherwise, I could have just already broken it down. Okay, so now at this point, we can just break down the work done by Fk to Fk delta x and then cos theta is equals to what? Half m bracket Vf squared minus Vi squared, right? Then again, note that the 0.35 that we are given here is not Fk, right? It is what? It is the coefficient. So that means if we are given the coefficient, remember, even from grade 11, Newton's second law, remember this work energy and power topic is just like a stretch of Newton's second law. It's just an extension of Newton's second law. So you still apply the concept of Newton's second law even here. Remember, to calculate Fk, you need to say it's nu k multiplied by the normal force, of which in this case, we can say that your normal force is just equal to your gravitational force. So that means here we are going to have 0.35 multiplied by, remember, Fg is what? Mass times gravitational acceleration. So the mass is what? 2 kg, the gravitational acceleration, 9.8. So we can just calculate Fk, 0.35 multiplied by 2 multiplied by 9.8. Then we are getting what? 6.86 newtons. And then we can replace it here now to say that this is 6.86. And then the displacement, that's what we are looking for. We are not using the 8 now because remember, we are done with A to B. We are now on the horizontal stretch here. We are now on the horizontal stretch. And as you can see with the question, it's asking us to calculate the distance. What is this distance that we are calculating? It's that same delta x. So we have delta x here, and then cos 180 degrees. Anything to do with Fk, the theta here is always 180 because Fk does negative work. Then it's equals to half. Mass is 2 kg. Final velocity until it comes to a complete stop, so 0. Initial velocity, that would be the velocity in which it reaches point B. So that's what? 6.92. Right? Because now we are starting from B, going to a point where it will reach a stop. So this, if we multiply this, it's going to be negative 6.86 delta x. And then umshinwe ibalo on the right-hand side, 1 over 2, and then 2 here, and then 0 square, minus 6.92, and then square, then close the bracket. Then we are going to have negative 47.8864. And we can divide both sides by negative 6.86, negative 6.86. Then your delta x is what? Divide that by negative 6.86. Then we have our delta x would be 6.98 meters. Hallelujah. Amen. Okay, so that's it. And then just like that, you have bagged yourself all that 13 marks, right? So very, very nice, very nice. Okay, let's look at another one. Let's look at another one. So yeah. Okay, so we have this one here. It says a 3 kg trolley is at rest, poliwe at rest. Then that means the initial velocity is 0 on a horizontal frictionless surface. A constant horizontal force of 10 Newton is applied to the trolley over a distance of 2.5 meters. Right? When the force is removed at point P, note that when the force is removed. So that means at this point, they are letting the trolley just move up at its own accord. No force is being applied. The force is removed at point P. So guys, whenever it comes to questions, you need to really read the statement. I know a lot of you are just so lazy to read the statement, but then that will only serve as a downfall, right? So you really need to read the statement and understand what's going on. If you have to reread the statement 2 times, 3 times, do so, because there is no answering the questions if you don't fully understand what's going on. So the trolley moves a distance of 10 meters up the incline until it reaches a maximum height. Now, this is a keyword, maximum height. If you can think of this based on your VPM, vertical projectile motion, you do know that once they mention maximum height, it means that at that point, the final velocity or the velocity is 0. So once they mention that an object reaches a maximum height or a projectile or whatever object, actually, if they say it reaches a maximum height, that means at that point, the velocity needs to be what? 0. That's why it momentarily comes to a stop, right? While the trolley moves up the incline, there is a constant frictional force of what? 2 newtons. A what? A constant frictional force. Let's note that. Of 2 newtons acting on it. Now 5.1 says, write down the name of a what? Of a non-conservative force acting on the trolley as it moves up the incline. If we can reread the last statement again, while the trolley moves up the incline, there is a constant frictional force of 2 Newton acting on it. So you can see that the answer is already there. In maths and physics, whenever they say write down, that means it's something that you can clearly observe from the diagram or from just reading the statement. It's never something that you need to really think deeply of. So write down the name of a non-conservative force acting on the trolley as it moves up the incline. It's what? Frictional force. 1 mark. And then 5.2. Draw a labeled free body diagram showing all the forces acting on the trolley as it moves along the horizontal surface. Read all the statement. Right. So I know a lot of people that just read one part of the question and then they start answering. Right. Make sure that you read everything. So a lot of you would assume that they would want you to draw a free body diagram for this part. And then you go again and you draw for the incline only to find that they said on the horizontal surface. So very important to read the statement. Then there we go. The horizontal surface is like this. And then we have normal force. We have a gravitational force. And then we have an applied force. Note that they said the horizontal surface is what? frictionless, no friction. So I'm not adding any FK there. We have force applied because at that point, while it's still there, a force is being applied. Remember, the force is not applied when it's now moving up the incline. So, but then here, we still have the force applied. So we have gravitational force Fg, and then force applied, and then normal force. Again, it's 3 marks, 3 forces. Okay, so just like that. And then now this was your 5.2, the free body diagram. And then in 5.3, state the work energy theorem. Again, you need to remind yourself by just writing the formula. W net is equals to change in EK. Then what does it say? States that the net work done. So this is what you do, guys. With these videos, I'm just trying to share with you the study method, right? So this is what you do. Go through your notes, learn everything necessary that you need to know, and then just keep on practicing as many questions as possible. The more you get to write those questions and then you start to observe the trend, it becomes very simple to answer exam questions. So states that the net work done on an object is equal to the object's change in kinetic energy. That's it. So work energy theorem states that the net work done on an object is equal to the object's change in kinetic energy. Then at this point, we have 1 plus 3 plus 2, which is already 6 marks, right? Okay, so now let's proceed. So we still in the battle, a luta continua. Then 5.4, use, you see this one, use the work energy theorem. That means you use any other energy principle, you get penalized, right? So this one is specifically saying use the work energy theorem. It's not saying use energy principles. If it says use energy principles, you've got options. But if it says use the work energy theorem, you don't have any options. You are only restricted to using the work energy theorem. W net is equal to change in EK. So that means even if you wish to use a WNC, you cannot use it here. Then 5.4, W net is equals to what? Change in EK. Then we are going to have what? Remember from our drawing, why do I keep on erasing this? Nah. Then Fg, and then force applied, right? So obviously, we already discussed that work done by Fn will be 0 joules, work done by Fg will be 0 joules. So there's no point in showing that. The only force that will be doing work is the force applied. So we'll say work done by Fa is equals to what? Change in EK. Now at this point, what are we trying to calculate? The speed of the trolley when it reaches point P. So we can break down this to Fa delta x and then cos theta is equals to half m bracket Vf squared Vi squared. And guys, it's just coming to me right now. I've seen this somewhere when I mark papers. People, they write like this: Vf minus Vi and then square. This is not the same as this. These two are not the same. Refrain from this. We don't know this. We have never seen this, right? The equation is like this. It's saying half m bracket Vf squared minus Vi squared. Don't be lazy to write that square and just say like, let me just take the square over here. It's the same as saying that. Remember, there's no such law that says if you have a square here, the square can go here and there, right? The square here simply means that in this case, it means that you have Vf minus Vi and Vf minus Vi, which is not the same as that one. It's no longer the same thing. That's a different case. So refrain from this. The correct notation is that, right? So I hope I'm clear with that. And then Your FA, what is the force applied? It's 10. What is the displacement all the way to point P? That's 2.5. And then cos, remember the theta here, because force applied is in the same direction as the displacement. We know that if they are parallel, that means the angle theta must be 0 degrees. So we have 0 here. And then we have half. Our mass is what? Mass should be, are we given 3 kg, right? So make sure every time you are reading the statement, I normally give you this strategy. Every time you are reading the statement, highlight your data so that you don't have to go back and reread the statement over and over again. Once you have highlighted the data, you are only just checking the statement to extract the data there. Then final velocity, is it what we are looking for? Yes, when it reaches point P. So VF squared. But then remember, it's starting from rest. So it's 0 here. So when we do this, that's 10 multiplied by 2.5 cos 0. That will be 25, right? And then half of 3, that's 1.5. So it's going to be 1.5 VF squared. And then obviously, if we take all of this multiplied by 0, that's 0. So we divide both sides by 1.5. Then it's 25 divided by 1.5, which will give us a VF squared is equals to 16.6667. You want to save this in your calculator. You want to save this in your calculator the way it is, and then immediately you square, right? So it's going to be, so you're just going to press on your calculator and then just square, and then there's a button just to the left of equal sign that says ans, right? So you're just going to have VF and then a square root of the answer so that you avoid having to round off that value. So 4 point, that's going to give us 4.08 meters per second, right? And then just like that, you have calculated the speed of the trolley when it reaches point P. Now it's even important to check if they want the speed or the velocity. You know, the difference is speed is a scalar, only has magnitude, but velocity has both magnitude and direction. So normally, if they just want to make you lose a bit of marks there, they will play around with those. So calculate the height h that the trolley reaches at point Q. Right. Now they're talking about height. When they're talking about height, and there's also friction there. Remember, at that point, friction is there. Now, I already know that if there's height and then there's friction, I am triggered to use what? Work done by non-conservative force. So I am for straightforward formulas, right? I do not want to choose a formula that will cause me to calculate a lot of things. I just want plug and play, right? Plug and play. I'm all about making things simple. Then WNC is equals to a change in EK plus change in EP. We're trying to calculate the height. Then work done by NC. If we can just try to draw the free body diagram here. Note, there is no question that says draw the free body diagram for the incline, but then it is very, very crucial that you draw the free body diagram so that you get to see all the forces that are there, right? It's for your own benefit. Drawing a free body diagram is not just about finding marks, but then it's also for your own benefit. You get to see everything that's taking place there. And then, okay. So perpendicular to the slope is your normal force. And then this is Fk. And then this is your gravitational force. If I'm using WNC, I can already identify that the only non-conservative force that I have here is Fk. So this will break down to work done by Fk. So I have Fk, delta x, and then cos theta. Cos theta. And then this is equal to half m Vf squared minus Vi squared. And then plus mg height finally minus height initial. Right. Okay, so Fk we are given, it's 2 Newton. So we have 2. The displacement from P to Q we are given is 10. And then anything to do with Fk, theta is always 180 degrees. And then this is half. The mass is what? The mass is 3 kg. Final velocity, they say when it reaches the maximum height at point Q. So we did mention that at maximum height point Q, that means the velocity there will be 0. And then initial velocity, that has to be the speed that we calculated at point P, which is 4.08 square. Then plus our mass is 3. And then here we have 9.8. And then check. Height finally, that's what we are looking for. The height at Q, which is H. So this is H. Height initially, noted that at point P, it was at ground level. So at ground level, the height is what? 0. Okay, then we punch this into our calculator, we get negative 20. And then punch all of this here, all the way to this point. So punch this first. So it's 1/2. We have 3 bracket 0 square minus 4.08 square, and then close the bracket. Now we have what? Negative 24.9696. And then we can do this one now. So I'm doing it separately because this one, as we can see, it has a what you call a constant there. Not a constant, a variable h. Variable h, 3 times 9.8. This is a plus 29.4h, right? So as you can see, we cannot add this 2 because this one has a variable h, this one does not. So this one is just a constant and that one is a constant, meaning I can take this and transpose it over to that side. So I'm going to have negative 20 plus 24.9696 is equals to the 29.4h. And then doing this one here, negative 20 plus 24.9696, this is going to give me what? Positive 4.9696, which is equals to what? 29.4h. Then I can divide both sides by 29.4 and then 29.4, so that I only remain with this h. Then h is going to be what? That 4.9696 divided by 29.4, this is going to give us 0.17 meters if I round off to 2 decimal places. So that is rounded off to 2 decimal places. And then, yep. So just like that, I have in the bag 5 marks and all in all, 15 marks, right? So that's basically how you were supposed to go about this question and the approach, right? So nice one. Nice one. Okay, so again, here we see another question. It says a 2 kg box is released from rest at point P, 5 meters above the ground. It slides down a smooth, frictionless surface. Note this, a smooth, frictionless, curved track PQ. So this is smooth. Say the diagram below. And then as we can see, it's smooth, but then from Q to R, it's now rough. Now, 5.1 says, state the principle of conservation of mechanical energy. Right. Now, what is mechanical energy? States principle of conservation of mechanical energy states that in an isolated system, the total mechanical energy is conserved or remains constant, right? Is conserved. So states that in an isolated system, the total mechanical energy is conserved. Now 5.2, they say use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. You see this one also, it's specific. Use the principle of conservation of mechanical energy. That means you cannot use any other energy principles. It has to be this one. If not this one, you get penalized. Then sum of EM at P will be equal to sum of EM at what? At Q. Sum of mechanical energy at point P is equal to sum of mechanical energy at point Q, right? So which means now I will have what? This breaks down, remember, to half mv squared plus mgh, because remember, mechanical energy is just the sum of the object's potential energy and kinetic energy. And then this is at point P. And then which is equals to half mv squared at point Q plus mgh at point Q. Now it's just plug and play. This is half. The mass is what? 2 kg. The velocity at that point released from rest. So it's 0. And then the mass is 2 kg, 9.8. The height at that point, we can see at point P, the height is 5. And then equal to half. Mass is 2. Velocity at this point, that's what we are looking for. Remember, use the energy, use principle of conservation of mechanical energy to calculate the what? The speed of the box when it reaches point Q. So that's what we are looking for, is the velocity at point Q. So let's just say v squared Q. And then plus mass is 2 kg, 9.8. But then what is the height when it reaches point Q? At point Q, it's on ground level. So that means the height at that point is what? 0. So obviously all of this will give us 0. So there is no need for us to punch it. And then we're just going to punch this part. 2 multiplied by 9.8 multiplied by 5. This is going to give us 98. Then what is half of 2 here? It's just 1. So we are left with v squared Q. This again will just give us what? 0. Okay, so if we are looking for VQ, you have to square both sides. And then what is square root of 98? Square root of 98 will give us velocity at Q will be 9.899, so just 9.90 meter per second. Right. Okay, so we have that. And then now they're saying the box passes point Q and moves 10 meter on a rough horizontal surface before striking a barrier at point R at a speed of 4 meters per second. Now, what are they saying? Use energy principles. So let's write the velocity at this point, 9.90 meters per second, because we're going to need it. So use energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. As it moves from Q to R. Now note this. We are going to start by drawing a free body diagram. As the object is moving through the draft surface, horizontal surface, and then this is going to be your normal force, your gravitational force, and then since there's friction there, it's opposing. We are not being told that there is a force applied here. So if you are not being told about the force applied, do not assume it's there. It's not. If there is force applied, they will tell you that a force is applied. So I know a lot of you that just assume that the force applied is there. It is possible for an object to just move at its own accord. Note that it's just sliding down. So if an object is sliding down, it's not being up. There's no applied force at it, right? No force is being applied to that object, meant to say. Now, okay, to then calculate the average frictional force, note again, we have a horizontal surface. And then you already know the energy principle that I like to apply if I'm working with a horizontal surface. It's obviously W net, right? So with the horizontal surface, I prefer to work with W net. Now, I prefer W net because it doesn't have any height. Unlike WNC, if you have a horizontal surface, you're just going to put change in EP, and then your change in EP will just be 0. So even if you were to consider WNC, and you say change in EK plus change in EP, basically because there is no height, then this one will just be 0, meaning it will fall off. Now you'd end up with this, which is the same as the W net formula. So rather just work with the W net formula instead of writing this when you're just going to cancel it anyways. So we already know that work done by Fn will be 0 joules, and then work done by Fg will be 0 joules. So the only force that is doing work here on the object will be the work done by what? Fk. So Fk will be the only force that's doing work. And then what kind of work? Negative work. So 5.3, going to say W net is equals to what? Change in EK. So your W net will only be represented by Fk. So break it down, it's Fk, delta X, and then cos it. So we are looking for that Fk, which is why we break it down. So half M bracket Vf squared minus Vi squared. Now Fk, we don't know what's Fk. Delta X, that's 10 meters. And then we have cos what? 180 degrees. Remember, anything to do with Fk, we have cos 180. Then this is half. Our mass is 2 kg. And then final velocity. Remember, they say it strikes the barrier at point R at a velocity or speed of 4 meters per second. So 4 square minus initial, that would be the velocity at point Q that we calculated previously on 5.2. So 9.90 square. And then now, pressa umshinwe ibalo, that's negative 10 Fk. And then we have half 2. And then we have 4 square minus 9.90 square, right? And then this is going to give us negative 82.01. Can divide both sides by negative 10. And then Fk is going to be what? So we divide that by negative 10. That's going to be 8.20, right? Newtons. So round off to 2 decimal places, or you can just write it as 8.201, right? Then either way, it's correct. So I just rounded off to only 2 decimal places as per exam instruction. Okay, so 4 marks just like that. Then I hope that makes sense. Then the barrier exerts an impulse of 40 Newton second to the left on the box when the box strikes the barrier. Calculate the change in kinetic energy of the box after striking the barrier, right? The change in kinetic energy. Now, they're talking about the impulse here. So the barrier exerts an impulse of 40 Newton second to the left on the box when the box strikes the barrier. Then calculate the change in kinetic energy of the box after striking the barrier. So let's note this. So in 5.4, we have a... Okay, so in 5.4, we have this. That's a F net. And then we have a delta T is equals to what? Change in EP. So we know that F net is what? Impulse, right? F net delta T, that's your impulse. So impulse, we know it to be equal to change in momentum. But then we are already given the impulse is 14 Newton second to the left. Now, if we are assuming that we take our right as positive, we know that we should indicate that as a what? As a negative. So that's negative 14. And then this will be mass bracket Vf minus what? Vi, right? Now, what we'll try to do here is to calculate the velocity, the final velocity after striking the barrier, right? So that's the velocity in which it bounces backward. Remember, the 4 meters per second is the one in which it strikes the barrier with, right? Now we want the one in which it returns, right? It rebounds from the barrier here. So we have negative 14, and then our mass is what? 2 kg. Final velocity, we don't know, but then we know that it strikes the barrier at 4 meters per second. We don't know the velocity in which it bounces off the barrier or rebounds off from the barrier. So, okay, that's that. And then we can just calculate simply by dividing by 2 both sides. And then we have negative 7 is equals to VF minus 4. Now, if we transpose the negative 4 over to the side, it's negative 7 plus 4 is equals to VF, which will give us our VF is negative 3 meters per second, right? So this is the velocity in which it bounces off, right? The barrier there. Now, to calculate the change in kinetic energy, we know that the formula for change in EK will be equals to what? Half M bracket VF squared minus VI squared, right? So it's just a matter of now saying half, the mass is 2. The final velocity is now the one that we calculated here, but then note how we substitute that. We need to say negative 3 and then square minus what? The initial velocity is what? 4. So that's 4 square. And then we simply just going to punch all of that into the calculator, half, and then 2. And then we have a negative 3 square, and then minus 4 square. Close the bracket. And then all of this will give us negative 7 joules, right? So that's negative work done. So our change in EK will now be negative 7 joules. That's basically how you were supposed to tackle that question there for 5 marks, right? So, okay, that's it for the lesson today. So hope you catch me for part 2, where I do even more challenging questions on work, energy, and power. So these are just the simple ones, but then there are even much more harder ones, which we're going to tackle on the next part of the video. But then I hope this one kind of gives you an idea as to what you should expect in an exam, right? So remember, it's your June paper now. So I don't think the work, energy, and power there would be that much difficult. But then, I always encourage that you practice more questions, and then always expect anything to come your way. So with all that being said, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.